Additive manufacturing is defined as a process that uses 3D CAD data to create a solid part, usually by printing the part layer by layer. Ultrasonic additive manufacturing is one subset of additive manufacturing. In this process, we use the power of sound, ultrasound, to bond thin layers of metal strip together to make a three-dimensional part. Right now you can see the ultrasonic additive manufacturing process in action. Thin layers of metal are rolled underneath of a welding sonotrode. The sonotrode vibrates back and forth and creates a solid-state ultrasonic bond. We repeat this process left to right, adding material as we go to build up a three-dimensional part. As you can see, periodically we can come in with 3-axis CNC machining to add different geometry to the part. This can include internal passageways and external shapes. Layer by layer, you add material just where it's needed with very little waste to build up the three-dimensional part. The process is driven all by 3D CAD, so you take your CAD model and put it into the system and out comes a three-dimensional part. The key differentiator between ultrasonic additive manufacturing and other metal additive manufacturing techniques is that it's a solid-state welding process. Solid state means the bond is created without melting the material. In fact, generally, our process happens at only 200 or 300 degrees F. Those are the highest temperatures we see when welding aluminum. Solid state is very important in that it gives you the ability to do many things. If you were to take and weld aluminum to copper using a fusion process such as arc welding, as that metal melts and then resolidifies, you get something that's called a brittle intermetallic. It has something with the properties of glass. With solid state welding, however, you don't create these intermetallics and you have a strong metallic bond without any loss of properties. This allows us to make metallic structures with multiple metals, almost at will. Any combination of metals that you want to create can be built into a three-dimensional part. The example on the bottom left is an example where we've embedded silicon carbide fibers between two separate dissimilar metals. As you can see, the fibers haven't been broken and we have a nice solid state bond between the materials. This is being used to make custom materials with custom material properties, such as metal matrix composites. The center is an example of cladding. We've taken copper and clad it onto aluminum. Cladding is often used to take an expensive metal A and bond it onto a cheaper metal B for things such as pressure vessels and corrosion vessels and oil and pipeline. We've done things such as tantalum to steel. Tantalum has about 10 times the corrosion properties of chromium and is very resistant to pitting corrosion. We've also done things like titanium to steel, where you want a thin layer of titanium to act as perhaps a diffusion layer or as a wear surface on otherwise steel structure. The example on the right is a custom material for armor properties. It's custom designed using layers of aluminum and titanium. As you can see, through thickness we vary the ratio of aluminum titanium to create a material with very specific mechanical properties. The properties at the front of this plate are different than the properties at the back, intentionally to create a good ballistic absorption material. Because ultrasonic additive manufacturing is a solid state process, we can also do things such as embed electronics, sensors, or active elements into a fully dense metallic part. The picture on the left is an example of embedding wires into an aluminum matrix. Although this is nice for metal matrix composites, in this particular case this is what's called a shape memory alloy. Shape memory alloys can change the amount of stress or strain in their material by simple changes in either magnetic fields or temperature. In this case, it's a temperature sensitive shape memory alloy called nitinol. We're using this to make a material with a coefficient of thermal expansion of 0. You add the nitinol into the aluminum matrix. As the aluminum heats up, it expands. However, over a specific temperature range, the nitinol, as it heats up, goes through a martensitic phase transformation and actually contracts. By varying the ratio of the two materials, you can make a material that essentially has a coefficient of thermal expansion of 0. The center example is something like an RFID chip. We've embedded RFIDs, electronic circuits, GPS, all into a metallic structure. Once we cover that up with a sealing metallic, you can have a tamper resistant or tamper proof part where all of your electronics are buried within a solid metal part where you can't get at them or damage them from machine turning or some type of activity that you would have in service. On the right, an example of a strain sensor. This is a fiber optic light being shone between several layers of aluminum. We've embedded things like fiber optic Bragg gratings that can be used as strain sensors, as well as strain gauges, thermocouples, and various other transducers that you'd want to embed. Again, we can embed these materials, these transducers, these sensors, in a solid metal part anywhere in the part that you want. So think about having, say, a engine block that has built-in thermocouples or built-in pressure sensors exactly where you want them to be. As with every other additive manufacturing process, UAM allows us to produce complex metal shapes that you wouldn't be able to make any other way with any other process. Because we're building one layer at a time, we can create very complicated shapes. We can lay one layer of material, which is typically on the order of 5 to 10 thousandths of an inch, and then come immediately after welding it and machine very fine features. The example on the left is a satellite component that has very deep and sharp channels built into it. Because we build this one layer at a time, we can come in with a very small end mill and make a very sharp edge in a three-dimensional buildup to make very fine features that are very tall and cylindrical and high. In the center is more of an aerospace product where we've built up material just where we need it. So in the aerospace industry, you often have the problem of buy to fly. That means you take a large, thick section of material and machine away 90% of it to make a component. Using additive manufacturing, you can take a thin plate and add material just where you need it so that there's not so much waste of billet material. The example on the right is a thermal management device. We do a lot of work with thermal management because we can combine different materials, but also because we can make small, complicated internal passages or microchannels. This is an X-ray of a part that we've built that shows very complicated internal channels that you couldn't make with any other manufacturing process. Another differentiator of ultrasonic additive manufacturing is the build rate, which greatly affects the build volume. This is a picture of our largest machine. It has a working envelope of 6 feet by 6 feet by 3 feet, which in the additive world is a very large envelope. We can build up to 60 cubic inches an hour if we're making a straight flat plate. For many of our armor applications and structural custom materials, we do this where we lay large sheets of material and weld continuously. This affords us the ability to make parts at about 60 cubic inches per hour. When we start doing shapes and parts that have complicated geometry, this quickly falls, but certainly we're typically in the range of 20 to 30 cubic inches an hour. All of our machines include integrated 3-axis CNC machining. This allows us to make parts to final net shape as we're building it. There's no secondary processing needed. Additionally, the 3-axis CNC machining affords the ability to make the complicated internal shapes that we've talked about previously. All of the machines are built using standard CNC technology, so tolerances as close to a half of a thou are easily achievable. UAM creates net-shaped solid metal parts using both solid-state ultrasonic metal welding and CNC contour milling. The process is both additive and subtractive. For the additive component, we have what we call an ultrasonic stack. It consists of transducers and a horn. On the left and the right, you can see a transducer. These are piezoelectric stacks that convert electrical voltage into mechanical motion. These transducers push left to right the center ultrasonic horn. This is an acoustically tuned device that is designed and built to vibrate at a very specific frequency, 20 kilohertz. It vibrates left to right at about 30 to 40 microns, creating a solid state weld. Our incoming feedstocks are typically 1-inch wide metal foils. The foil thicknesses can range from as thin as 1/1000th of an inch to as thick as 20,000th of an inch, depending on material properties. Because we are adding material in 1-inch increments, we often have geometry or geometric aspects that are smaller than 1 inch. To remove the little bit of excess material that we have, we use CNC contour milling. It's a standard 3-axis CNC mill to remove material to get to final net shape inside the machine all at once. Ultrasonic spot welding is a metal welding technology that's been around since the mid-60s. It's used widely in electronics and small packaging to weld spots or small areas of thin metal films together. What we've done with ultrasonic additive manufacturing is take this ultrasonic spot weld and make it a continuous process with a continuously rotating ultrasonic horn. It's a disc that rotates and rolls over the foil material as we want to bond it. The ultrasonic bond is well understood as it's been, again, the technology's been around since the mid-60s. What's happening is the ultrasonic horn vibrates back and forth. This takes the ridges and the valleys. I don't care how finely you polish a piece of material, there's always ridges and valleys. It vibrates those ridges and valleys together. Now, metals in general like to bond to one another. If you were to take two perfectly clean pieces of metal into outer space and push them together, the metals would actually form a joint all on their own. It's called diffusion bonding. What prevents diffusion bonding here on Earth is the oxide layer that's inherent to every metal surface. So what we do is we take and vibrate those materials left to right. It takes the ridges and valleys and rubs them together and actually rubs that oxide layer off. It breaks it up into small tiny pieces, exposing virgin metal on virgin metal. Because we're providing just a little bit of temperature and a little bit of pressure, we get a solid state bond between those two materials. Now the question is always asked, what happens to that oxide layer? Well, unfortunately, the oxide layer isn't totally destroyed. It's still there in the bond. We typically see it as small particles or gravel inside a micrograph, about 150 microns either side of the bond joint. And this does have an effect on material properties. In the X and Y direction, we can typically get wrought material properties of the incoming foil. However, in the Z direction, we typically take a knockdown of 5 to 10%. So we lose 5 to 10% of the normal material properties in the Z direction because of this oxide layer. So we have this ultrasonic rolling horn that's welding materials by vibrating side to side, rubbing off the oxide layer, and creating a solid state bond. So how do we build up a part? As you saw in the video, we take this process and we just move it left to right. Tapes are laid side by side and then build up layer by layer, similar to a bricklaying pattern. People always ask, well, what about the joint between the two tapes side to side? Why are those not failing? What we actually do is overlap the process by about 1/1000th or 2/1000th of an inch. By doing this, we actually extrude metal into that void where the two tapes overlap and actually create a solid state bond. One of the unique aspects of high power ultrasonics is that it greatly reduces the flow stress of a material when it's under the high power ultrasonic field. So this allows us to extrude that metal very simply and fill in those voids and actually get solid state. All of the 3 UAM machines that we build are controlled using standard CNC controls called G-code. This allows us to use very standard industry products and to teach people how to use our products in a very short amount of time. If you have a CNC operator who knows how to run CNC mills, we can teach them to run our machine in just a couple of hours. In order to get from CAD to solid part, we have to create the G-code though for the CNC. So what we have is a product we call SonicCam. SonicCam takes a 3D model, slices it into layers, and creates the G-code needed to drive the machine. In the background of SonicCam is really a software package called Delcam. Delcam is a commercially available CNC machining program that has several 100,000 seats available worldwide. Delcam is used to tell a CNC machine where to machine away material out of a solid block to make a part. It says, I have a 1-inch end mill, I want to take 6th thou layer off, and it has algorithms to figure out where to move that 1-inch end mill to make the part that you want. What we're doing is we're actually adding a couple hundred lines of code on top of Delcam that come in and reverses the polarity of the sign. So instead of saying we have a 1-inch end mill and we're going to remove 6th thou at a time, we say we have a 1-inch end mill and we're going to add 6 thousandths at a time. This basically allows us not to be a software company. We can use the ready-made algorithms that Delcam provides, inverse them, and we have a 3D CAD package. So for all the metallurgists out here, here's a little more information on how the actual ultrasonic bond is being formed. As we said, we've studied the process of ultrasonic metal welding for years, and we believe the bonding mechanism on our process is, in fact, dynamic recrystallization. When you take large grains, such as seen in the top left picture, and you shear them at a very high rate, their surface energy requirements actually changes under high shear. And the surface energy and thermodynamics drive a preferential grain size that is much smaller. So what happens is the large grains recrystallize very quickly into very, very small nanograins. What we think happens is because of the high shear rate, create small nanograins. Because we have a little bit of temperature and a little bit of pressure, those grains quickly grow, and they grow across the interface such that there is no more interface. Again, the picture at the top left, you can see large grains, which are in fact the grains of the foil that we're using to weld together. However, at the center, at the bond line, you can see small grains. Again, these grains are, you can see, so they're not nanograins, but we think the dynamic recrystallization creates nanograins that grow. These are more on the order of about 100 micron. We can see further evidence of that if we look at the crystallographic orientation of the grains. The bottom right shows two different pictures. One is of the bulk tape, and you can see the colors in orientation imaging microscopy. The colors indicate the crystallographic direction of that grain. You can see that you have pretty homogeneous grain directions. The crystals are all green, they're all kind of in one direction, which you expect from a rolled product, which this is. However, at the bond area, you can see that we have crystallographic orientations that are all over the map. And again, we have much smaller grains. This is more evidence that we are indeed creating new grains through dynamic recrystallization, and that they have in fact grown across the interface. So to touch upon it one more time, solid state additive manufacturing allows us to bond dissimilar metals together. Now this chart is not for ultrasonic additive manufacturing. This chart was made for ultrasonic metal welding. However, we've found that all the different materials that we've tried that you can weld with ultrasonic metal welding, we can in fact weld with ultrasonic additive manufacturing. So to give you an idea, in the micrograph here you can see aluminum, copper, and silicon carbide fibers all together in a matrix. We've done things like aluminum to steel, aluminum to titanium, titanium to steel, tantalum to steel, amongst many other combinations. The idea here is that you can make custom materials by combining dissimilar metals almost at will. The only thing that I'd add is that no matter how good the ultrasonic bond is, if you have large differences in electronegativity, you can create a battery and create corrosion problems. So you still have to be careful about what metals you combine so that you don't create a battery and corrode the part away. So Fabersonic's business model is in fact to make parts for customers, as well as to build machines and custom machines for people to use the ultrasonic additive manufacturing process. Here are pictures of our three products that we are currently selling. The picture on the left is of our SonicLayer R200 platform. This platform is optimized for research institutions that just want to play with the ultrasonic additive manufacturing process and don't need to make large parts. In fact, this system does not have CNC machining built into it. All it can do is raster a weld head over layers of metal to weld material together, but we find this is very useful for universities. The first one of these was built and delivered to University of Louisville, and we're currently building another one for another research institution. The center picture is the SonicLayer 4000, which is a CNC machine upon which we've added our welding technology. It has a pretty large bed with an area of 40 inches by 24 inches and a height of about 24 inches as well. It has integrated 3-axis CNC machining, a load capacity of about 2,500 pounds, and can be outfitted with either a 4.5 or a 9 kilowatt welding head. The first machine of this was delivered to Ohio State University, and we're currently building a second machine for another client. The largest machine on the right is the SonicLayer 7200. Currently this is installed at Fabrisonic's facility in Columbus, Ohio. Again, a CNC 3-axis mill with added ultrasonic metal welding technology. It has a load capacity of 5,000 pounds, 9 kilowatts, and is the largest of our machines with an area of 72 inches by 72 inches. This machine can be highly customized to build larger parts, and also has the capability of 5-axis ultrasonic additive manufacturing welding. This can be used for repair applications. We can come in, take a very large part, say the front of an aircraft engine. We can machine away a damaged surface on, say, a precipitation hardened aluminum alloy, where if you were to weld on that aluminum alloy with arc welding, that you'd wipe out the properties. Using this machine, we can machine off and then with 5-axis welding build that material back up. Because it's solid state, we don't have any effects to the microstructure of the aluminum, and we can build that back up as a repair.